Hello, my dear students, and welcome back to the second part for lecture number 3, dealing with MOSFET. In the previous part, we have dealt together with what's called the DC analysis for our MOSFET, where we have solved two examples in order to investigate how we can determine all the voltages and the current in a MOSFET circuit under a DC bias. Now, in this part, we are going to demonstrate the AC analysis of MOSFET. If you remember in the first part, I have mentioned that there is no AC analysis without a DC analysis. Why we need a DC analysis and AC circuit? This is simply because a MOSFET circuit cannot operate with only an AC source. This is very simple, and you can easily recognize it. Now let's assume that this AC source is connected to the gate. As you know, let's, for example, assume that this is a sinusoidal source, which means that as far as this is a sinusoidal source, so you can simply say that, okay, this is a source where, let's draw an x-axis and a y-axis, and then a sinusoidal source is a source that oscillates in this manner. Okay, so but we also know that in order to make this MOSFET on, the voltage applied on the gate should be greater than V threshold. Otherwise, your MOSFET will be off. So if you just connect an AC source to the gate of a MOSFET, that simply means that whenever your voltage is smaller than V threshold, which is actually this, I assume that this horizontal line I just drew is at V threshold. So in this region, your MOSFET will not operate. The MOSFET will operate only in this region, because in this region, the voltage is greater than V threshold. Otherwise, the MOSFET will not work. That means that you will have a problem with the operation, because the MOSFET will operate only, let's say, 40%, 35% of the time. And the rest of the MOSFET will be off. Accordingly, you will never find an AC circuit with a MOSFET without a DC bias. So this DC biasing is the key point in order to ensure that your MOSFET is working before imposing an AC source to your AC circuit. So let's make it in another way. I will start to use my method. Let's do it. So this is our MOSFET gate, and we have assumed first that we are connecting an AC source. That looks like that. And let's say that this is the ground, this is the source, this is the ground, and this is the gate. Okay, let's say that this sinusoidal input is 0.5 sine omega t. Then what you are going to do is that, let's plot it. So this is the VGS, and it looks like it. And this is 0.5, and this is negative 0.5. Perfect. Then, if I told you that V threshold is equals to 1 volt, accordingly, this MOSFET will be off all the time, because the maximum voltage applied to the gate is just on 0.5. And then this input will not reach the required voltage, which is V threshold, and accordingly, your MOSFET will be turned on. So how we can make our MOSFET turn on? Very simple. the same MOSFET. Again, the source is grounded. Herein, you have your AC source, which is still 0.5 sine omega t, but it's now series connected to an DC source of, for example, 2 volts. So the overall voltage here, the overall voltage applied to the gate now is 2 plus 0.5 sine omega t. So this voltage, if you would like to plot this voltage, it will be similarly like this one, but it's shifted to 2. As you know, the sinusoidal is varying from positive 1 to negative 1. So this resultant will vary from 2.5 to 1.5. So let's plot it here. So I will plot here. This is the 2, which is the shifted value, and then you will have something like that. The maximum value will be 2.5, and the minimum value will be 1.5. Accordingly, the MOSFET will work 100% of the time because the minimum voltage is 1.5 and the V threshold is 1 voltage. So the minimum input gate voltage is still greater than the threshold voltage. That's why your MOSFET will work properly. So this is the first important information, that no AC input without a DC biasing. We call this a DC biasing or a DC offset. Maybe, I don't know if you hear this word before. So we shift the input with a DC offset, which is now 2 volts, in order to guarantee, in order to ensure that our MOSFET is working all the time, regardless the value of the AC signal. Okay, so this is the first important information concerning the operation of a MOSFET and the need for a DC circuit in order to connect them. But accordingly, as you can see, we have here 2 sources connected to the gate. So let me so this is our circuit. We have 2 sources connected to the gate. An AC source, which is our real input, our signal, and a DC biasing in order to offset the AC input and to ensure the operation of a MOSFET. Okay, let's call this RD. Let's call this VDD. And of course, this is the drain, and this is the source, and this is it. Accordingly, in any AC circuit for a MOSFET, you are expected to solve it 2 times, because simply what we are going to do is that we are going to enroll what we learned in the circuit under the title superposition. We are going to superposition these two sources. So in the first stage, you will neglect this AC source, considering it as a full circuit, and you will solve the circuit only with a DC source, which is typically what we learned in the previous part under the title DC analysis, whenever the gate has a DC input. That's why I told you that in order to solve an AC circuit, you need a DC analysis. This is the first stage. Then the next stage is that you will disconnect the DC as a short circuit and you will solve it as an AC source, which is the AC analysis, which is our target. But before going into the the AC analysis, which is the main target of this part, let's first start with considering a more investigated way in order to understand the DC analysis. As you can see, here we have an input, which is VGS. And let's say that we would like to have some sort of a KVL over this loop, because simply this VDD is connected like this. So, sorry. So you can make a KVL over this loop. This KVL will result with VDD, which is the source, equals to ID times RD, which is the current flowing here in this resistance, plus the voltage drop here, which is VDS. Okay, we can rewrite this equation in a form that ID equal minus VDS over RD plus VDD over RD. This is another equation. Perfect. Done. Why I'm rewriting this equation in this form? Because usually in our IV characteristic curve, if you remember, we are considering the ID on the y-axis and VDS on the x-axis. If you remember the IV characteristic curve, let me put it here. So let me use another color. For example, this one. So if you remember these curves, representing on the x-axis VDS and on the y-axis ID. Okay, accordingly, this is the IV characteristic curve, which is related or reflected to a certain MOSFET. Now we have another equation, which is ID versus the VDS again. So we can plot this equation. By the way, this is a very simple linear equation. If you put ID equals to 0, then you will have VDS equal VDD, which is this point. So this is why ID equals 0. So whenever y equals 0, then this is the point. And if you put VDS equals to 0, then you will have ID equal VDD over RD, for example, this one. And as far as this is a straight line, so what you are going to do is just, you are going to link this together. This, what we call, my dear students, the load line equation. The load line equation is the equation extracted from a KVL analysis over the drain source branch. It's usually an equation linking the ID with the VDS. Then, by plotting this equation, you can reach what we call the operating point of a MOSFET. How? This family of curves, if you remember, my dear students, is plotted with respect to the different values of VGS. So, for example, this is for 1.5 VGS, 2, 3, 2.5, 3, 3.5, and so on. Okay, so if you started to do a DC analysis, then you are considering this voltage, which is, for example, 2 volts. Then your operating point is simply the intersection point between the IV curve with the typical VGF, which is 2, and your load line. And we call this the operating point. So simply, the operating point is the intersection point between the load line and the IV characteristic curve with the VGS used. Whenever your VGS changes, then your operating point will change based on this equation. So you have a set of intersection points, then you can move across these intersection points based on the variation on the VGS. Okay, so let's see it in a better way by turning to our PowerPoint slide. Okay, so that's now we are back to the presentation slides, and then this is the equation. This is the load line equation. Of course, this is not a standard equation because simply if I add an RS here, which is a a source resistance, this source resistance will be added to the equation. So this equation can vary. However, in all cases, this is a KVL equation across the source or the drain source branch. This is the standard procedure. And now this is what we call the load line. This is what we call the IV characteristic curve. And then the intersection point is the point which represents the operation point. Okay, so in order to investigate the impact of the AC source on this system, let's say. So for example, let's say that this is a 2 voltage source. So what you are going to do here is that you are going to go to the curve for 2 voltage, for VGS equal to. So let me, for example, highlight it by this. So let's say, for example, this circle represents the operating point at VGS equals to 2 voltage, which is an intersection curve, an intersection point between the load line point and the VGS, the curve where VGS is equal to 2. Okay. Now, when you insert this AC voltage, which let's assume again, this is an 0.5 sine omega t. So this will mean that your VGS will fluctuate between 1.5 and 2.5, if you remember the example. Accordingly, what will happen is that you will have a variable operating point that will vary between 0.5, let me use another color, that will vary between 0.5, sorry, 1.5 and 2.5. As far as the VGS is varying, then you should expect simply that the ID will vary because ID is a function in VGS. So whenever you have a varying VGS, then you have a varying ID. And whenever you have a varying ID, then you're having a varying VD. And this is typically this. This is the input. You have a VGS, which is fluctuating around a certain DC value, it depends on the value of this source. And then you have an output, which looks like this. Accordingly, which is the target of this session, we can use our MOSFET as an amplifier. This is the input voltage, which is the VGS voltage. And this is the output voltage, which is the VDS voltage. So the output voltage can be amplified. I mean, can have a larger amplitude with respect to the input voltage in a very easy manner. Now, what we are going to do is that we are going to express first in equation, then by examples, how the MOSFET can work as a voltage amplifier. Okay, so let's start this journey together. I will return back to my whiteboard and let's start it together. So this is typically our circuit. This is the gate, this is the drain, this is the source. And in order to distinguish in a terminology between the DC voltage and the AC voltage, we will usually use V small to indicate the AC sources and V capital to indicate the DC sources. And again, the same will be implemented also for current. So I small for AC and I capital for DC. This is maybe the most standard way in order to make a distinguishing between an AC and DC value. Okay, so if we can say that in a very easy manner that our total VGS is equals to V capital GS plus V small GS. So it's that the voltage applied to the gate, because the source is grounded, the voltage applied to the gate is the sum of this V capital and V small. Okay. If you assume that your MOSFET is operating in the saturation region, then you can write an equation. We already studied this equation in the first part, which is ID equals to Kn dash W over 2L VGS minus V threshold all square. Now, this VGS is the total gate voltage applied, which is actually VGS total, which is this term. So you can write the equation like that. ID equal Kn dash W over L, and then you have VGS, which is the DC component, plus V small gs, which is the AC component, minus V threshold all squared. Perfect. Now let's break down this bracket. However, while we are breaking down this bracket, we will consider it like that. The VGS, let me use another color. The VGS and V threshold will be considered one term, and V small gs will be considered the other term. Why I distinguish it like this? Because simply V capital GS and V threshold are DC voltage, while V small gs are an AC voltage. So I will break down this bracket in this manner. So ID equals, there's two here. So first we have Kn dash W over 2L. Then the first term will be V capital GS minus V threshold all squared, which is, for example, X squared. So let's call this X and this Y. So it's X squared plus 2XY plus Y squared. So this is X squared, which is VGS minus V threshold all squared. Then plus 2XY. So Kn dash W over L. I will cancel the 2 because it's 2XY, so 2 cancelled by 2. Then we have VGS minus V threshold multiplied by V small gs. This is the X term and this is the Y term. Plus the third term is Kn dash W over 2L V small gs all squared. This is simply the breakdown of this bracket into X squared, 2XY, Y squared. Now, let's start discussing this out. This ID current is the composition of 3 components. The first component is a pure DC component. Kn dash W over 2L. Kn dash W over 2L is a constant, and VGS capital is a DC, V threshold is a DC, then it's a pure DC component. So as far as we are implementing an AC analysis, we can neglect any DC component. How we can neglect? It's very easy, my dear student. You can just add a capacitor here in the output. If you just add a capacitor here, and you know that capacitor will not pass any DC current, because simply in a DC analysis, capacitors are open circuit, so current is equal to 0. So this capacitor on the output will get trapped out of any DC component. So simply, this current is not of interest. It's a DC current. Accordingly, we have two AC current components, the second and the third. The second, which is V capital GS minus V circle times V small gs, and the third, which is VGS small o squared. Both are an AC component. But if you remember my example, here, let's do it. I think, yeah, this one. If you remember my example, we said that, for example, we have an input of 0.5 sine omega t, while the DC is 2 volt, which is actually not something by chance. This is something somehow standard, that the voltage, the DC voltage, VGS, all the time will be somehow much greater than V small g. Accordingly, in this equation, you can say that V capital GS minus V threshold is much greater than VGS small, which means that you can neglect this term with respect to this term. Of course, my dear students, this is an approximation. In reality, this term exists. However, in order to make our study a bit easier in a mathematical way, we just neglect the second order term and keep it a linear equation. Accordingly, we can rewrite our ID equation so that ID equals to Kn dash W over L V capital GS minus V threshold over or times V small gs. Now, this is an AC current, so it's better to write it I small b, because this is an AC current. So this AC current is proportional to the AC input. The higher the gate, the higher the gate voltage, the higher the output current. And this relation has a constant, which is Kn dash W over L VGS minus V threshold. And don't forget that V capital GS is the DC offset or the DC biasing for the gate. Now, this is a gain relation, an amplification relation. And the constant of this amplification is this Kn dash W over L VGS minus V. We call this what we call GM, or the MOSFET transconductance, which is the relation between the current and the voltage. This is the input current, which is VGS, and this is the output voltage, which is ID. The relation between these two terms is GM, where GM is simply equals to Kn dash W over L VGS minus V threshold as a constant. So let me now return back to the slides. Okay, so this is the output. This is the transconductance with linking the voltage here with the current. Accordingly, we can use this equation to model our MOSFET in the saturation region as a current dependent, sorry, a voltage dependent current source. We already have reached this conclusion before, if you remember. If you remember, my dear students, while we are considering the MOSFET here in the saturation region, I told you that we can consider it as a voltage dependent current source. But now we have a more simplified version of the equation, which is this term. Okay, so whenever you of course, as you can see, GM is a DC term. It's Kn dash W over L VGS minus V threshold. So whenever you start the AC analysis, you first have to calculate this GM and insert it in this equation. And now you can know, now you can calculate your AC current, knowing that the AC current is equal GM times the VGS of the AC source. And again, if you remember, we can modify the model to be like that whenever we have what's called the output resistance of a MOSFET, which is due to this slope. But before proceeding to our main example to solve this circuit together and to calculate the different parameters, I just need to answer a question that may come to your mind. You told us, or I told you, that you should have an input voltage and an output voltage. This is a voltage amplifier. But this relation is a relation linking a voltage to a current, not a voltage to a voltage. So actually, the answer is very easy. Let's go to this branch. The VD is equals to what? You know that VDD minus VD equals to ID times RD. So this is simply mean that the VD and the ID are linked together. Whenever you have a change in ID or the drain current, that will automatically attribute to the V drain. So this relation, which is a relation between VGS and ID, can be turned into be a relation between a VGS and VDS. And accordingly, you can calculate the gain of this MOSFET amplifier, as the VDS is the output voltage and the VGS is the input voltage. And this is what we will typically do in the coming exam. So let's now turn to this important exam dealing with a MOSFET. This is a standard question in any electronics exam, to have an AC MOSFET working as an amplifier, and then we calculate together different parameters related to this. So for the shown amplifier, determine the small signal voltage gain, which is the input gain or the input voltage over the output voltage, and the input resistance. And the transistor has the V threshold is equals to 1.5 volts, Kn dash W over L equals to 0.25 milliampere over volt square, VA equals 50 voltage, which is voltage applied to this point. Assume a coupling capacitance to be sufficiently large so they act as a short circuit at the signal frequency of interest. So these two capacitors are a short circuit whenever they are an AC, and they are an open circuit whenever there is a DC. Okay, so I will start first by just copy paste the circuit in our whiteboard, and then we will start together the journey of solving this circuit step by step. Again, this is a very important example in our module. Okay, so let's start together the solving procedure. As I told you maybe in part number one of the main advantages for the MOSFET circuit is that it has a constant procedure, a fixed procedure, regardless the circuit's structure or topology. The procedure or the solving procedure is constant, is the same. The first step after you copy paste the circuit in your exam paper is to start the DC analysis. What are the main key parameter in the DC analysis is the capacitors. In DC analysis, capacitors are open circuit. So the circuit in the DC is just limited from here to here. This is your DC circuit. Now, this is the circuit we are going to solve. So as a first step, usually my recommendation is to replot the circuit again, considering only the DC component. So you will have I think this will be the circuit. Again, let's check together. We have a resistance, and then this is connected, and this is the source. This capacitor is open circuit, this capacitor is open circuit. So as values, this is a 10K, and this is a 10 mega. Of course, this is a drain, this is the source, and this is the. If you remember, my dear students, my tips during the part number 1, while dealing with the DC analysis, that the current flowing to the gate is equal to 0. So this current, IG, is equal to 0. As far as you have a resistance with the current is equal to 0, that means that this is a short circuit. So this resistance has no meaning in the DC analysis. So this is a short circuit. This is a short circuit. And this has no meaning. Now, please remember this connection. Connect the drain to the gate, which means that VGS is equal to VDS. Then, as far as you recognize this link in the circuit, you can easily say that your MOSFET is in the saturation. If you remember, we did it together while we were solving the current mirror circuit. Now, you can write an equation for the ID or for the drain current in a very easy manner, saying that ID equals to Kn dash W over 2L times VGS minus V threshold whole square. If you return back to the head of this question in the fraction, you will find that Kn dash W over L is given, which is 0.25 milliampere per volt square. V threshold is given, which is 1.5 volt. VGS equal VDS. So you can write it VGS or VDS. Both have the same meaning. Or even you can write it VD because S is ground. So it's just a V. Accordingly, I can rewrite the equation in this. So it's 1 over 2 times 0.25 times 10 power negative 3 times VD minus 1.5 whole square. Now, this equation is the one equation in two unknowns. If you remember, we faced the same challenge while solving our DC circuits in part number 1. Herein, this is the maximum that you can get from the MOSFET. You have to return back to resistance to the circuit and to find another equation that links ID with VD. And of course, the solution is very easy because you only have a single resistance in this circuit. So there is the only way to find this equation in this resistance. So in a very easy manner, you can say this is a VDD, which is 15 volts. So you can say that VDD minus VD equals to ID times R. This is a very simple equation, which means that 15 minus VD equals ID times 10 times 10 power 3. Or you can easily say that here, let's write it, that VD equals 15 minus ID times 10 times 10 power 3. This is the second equation. And this is the first equation. Now you have two equations by two unknowns. What you are going to do simply is substituting by this term herein and start having a second order ID equation, which is again will result with two values for ID. If you remember, this is typically the same what we did in part number one, if you remember, my dear students. So by going to these output, let me go to check what will be the values. I already did it before, so we will have an ID. Okay, so here actually I solve it in terms of VD not ID, which is of course the same. So I get two answers. VD equals 4.4 volt and VD equals negative 2.2 volts. Then, of course, without any thinking, the first solution is right, the second solution is wrong. This is simply because, if you remember, my dear student, in order to have your MOSFET working, should have a positive VDS. The voltage on the drain should be always greater than the voltage on the source. As far as the voltage on the source is grounded, then the voltage of the drain should be positive. So the negative solution will be the wrong solution, and the positive solution will be the right solution. So VD equals 4.4 is the solution. Accordingly, you can calculate ID, which will be 1.06 milliampere. So now this is ID and this is the VD. Okay, so is this a termination for the DC analysis? No. In order to terminate the DC analysis, you should end it up with calculating what we say or what we call the GM, the transconductance. I will turn back to find it somewhere in my previous slide. Yes, this one. GM equals Kn dash W over L VGS minus V session. This is the terminating point in calculating the ID, or sorry, in calculating the DC analysis step. So at the final stage, you say the GM equals to Kn dash W over L VGS minus V session. Now you should have all these terms. Kn dash W over L is a constant, which is 4.25 times 10⁻³ and VGS, which is the same like VDS, which is 4.4 minus 1.5. So you can easily do it like this, and you can say that now the GM equals to 0.725 milliampere per volt. Now this is the termination for the first portion of the question, which is a DC analysis. So let's agree that the termination is VD, ID, GM. You should calculate all these three steps using your DC analysis part. Okay, so now let's go to the second stage, which is the AC analysis. Now I will return back to the main circuit. This one, which is our main circuit. In the DC part, we considered, if you remember, capacitors as an open circuit. That's why we get fed out of this input and out of this output or load resistance. Now, in the AC analysis, we will going to consider these two capacitors as a short circuit, and we will start together the journey of solving this AC circuit. So, as we did in the first part, the first requirement in this stage is just to replot the circuit in the AC format. So we'll consider these two capacitors and a short circuit and write the same or plot the same circuit again. Here. Okay. Before continuing, let's stop a while. Now we have this. This is a 10 mega. This is a 10 kilo. This is another 10 kilo. This is the input. This is the drain. This is the gate. And this is the source. What about here? This is a VDD. But please don't forget, VDD is a DC voltage. And now we are considering the AC analysis. That's why I will going to shortcut this VDD and replacing it with ground. So why is this? Because now I am superpositioning all AC inputs. We have only one AC, which is this one. So any DC should be grounded. That's why here this is short circuit or grounded. So now we don't have VDD, it's a DC voltage, and this is ground. Okay, so this circuit represents the AC circuit for a MOSFET. We only have AC sources, which is this one. This is the input and this is the output. So this is V out and this is V in. And we are now considering the relation between the input and the output. Okay, perfect. So in order to solve this AC circuit, we have to return to what we call the small circuit model. Please don't forget this model with voltage dependent current source. That's now in this region, in this in the second or the bottom half of the page, I will going to reflect this MOSFET onto a small circuit model. Okay, so the first step, as I mentioned, is to reflect this circuit into a small circuit model. How are we gonna do this? First, we'll sketch the small circuit model without your circuit, the standard small circuit model, which looks like that. So we have the gate, and usually we have a common source, which is ground, and we have here the drain. Between the drain and the source, we have a current source, which looks like this, which has a value equals to Gm times V small gs. And this is the VGS. So this is your standard model. This model can also include what we call the output resistance, R node. This R node, if you remember, is an output of the channel modulation effect. There is a way where you can calculate this R node. However, within the scope of this course, we will not consider this. So it will be given in your exam. For example, in order to make the problem more challenging, I will consider this R node equals to 47 kilo. So now this is the standard model. This model will be constant regardless of the circuits. I will start now adding the circuit component, but this is the standard model. We have a gate and the source. The voltage between the gate and source is V small gf, which is an AC input. In the drain and source, you have two elements connected. You have a voltage dependent current source, which is Gm VGS, and you have a resistance. This resistance may be considered and will be given. Otherwise, if it's not given, you will assume that this is equals to infinity and it's an open circuit, and you will neglect. This is simply like that. Okay. Now you will start connecting the circuit element, the additional circuit element, to your small circuit model. So I will use another color in order to make it, just to distinguish. So for example, If we start with the gate is connected to the input. So here we have the input. So as you can see, the input is typically the VGS. Okay, and you have a resistance between the gate and the drain, which is 10 mega. Okay, what about the drain? The drain is connected to a resistance to the ground, which is 10K. This one. And another resistance to the ground, because don't forget, we have short circuit the VDD. So this is the overall circuit model. The red part is a constant part, regardless of the circuit. And the black part is dependent on the circuit. So this may differ from one circuit to another. What we are seeking for? We are seeking for the small source voltage gain. What is the small voltage gain? Is the relation between this V out and this V in. We are seeking for the relation between V out and V in, or V output over V in. V output over V in is the gain. So let's see together now how we are going to solve this circuit in order to get a relation between the output and the input. Okay, perfect. So in order to proceed, let me just replot this circuit in a more cosmetic way. It will be typically the same, just will copy it fast. So we have here the gate, and this is a common ground. So this is the V input, which is the same like VGS. Then we have this resistance, which is the 10 mega resistance. Now this is the gate, don't forget, and this is the drain. The drain is connected here with a voltage dependent current source, which has a value GM times VGS, which is now the input. And then we have 3 resistors in parallel, which are the 47K, the 10K, and the 10K. And now this is up here. Again, what we are seeking for is to get a relation between the V input and the V output. And basically, it's a very basic, a very easy relation. Let's see. So, if you recognize here, we have a current source. This current source will conduct a current that's going to flow in 3 resistors, as you can see. So now this current is going to flow here, here, and here. So the voltage here, the voltage between these 2 points is simply what? Is the current times the equivalent resistance. The current is GM input, so V output equals GM times V input, which is this current, flowing in the parallel combination of the 47K, 10K, and 10K. But please check the polarity. Here the current is flowing from bottom to top, while the voltage here is positive negative. So the voltage here is negative with respect to this polarity, so we have to add a negative sign. So V output equals GM times V input times the parallel equivalent of these 3 resistors. Accordingly, the gain, which is V output equal V input, equals to minus GM times the parallel equivalent of 47K, 10K, and 10K. GM we already calculated, it was 0.725 milliampere per volt square. And here we have these values, and this will result with negative, I think, let me check, I think 4.3. Yeah, no, 3.3. negative 3.3. Of course, the gain is dimensionless because it's voltage over. So you can very easily, you can calculate the overall gain of this resistor. Okay, this is the first requirement in the AC. What is the second? The second was the input resistance. So if you are considering the resistance from this point, what will be the resistance? So basically, the resistance is voltage over current. Here, the voltage is V input, and the current, let me call it I input. So in order to calculate the input resistance, it's simply V input over I input. V input is the input voltage, of course. But what is the I input? I input is the current flowing is this 10 mega ohm resistance. This current is equals to what? This current is equals to the voltage here minus the voltage here over the resistance. The voltage here is the gate voltage, which is the input voltage. And the voltage here is the drain voltage, which is the output voltage, over the resistance, which is 10 mega. So I input equals to V input minus V output over the 10 mega resistance. You can easily substitute it here. So R1, R input equals to 10 mega times V input over V input minus V out, as you can see. Perfectly. So how can we solve this? Let me write it again. So R input equals 10 mega times V input over V input minus V out. Okay, equals 10 mega ohm times. What if I get this V input common factor and I have it 1 minus V output over V input? Now V input will be cancelled with V input. V output over V input is what? Is the gain, which we just calculated. So the R input equals 10 mega ohm times 1 over 1 minus A is just calculated with negative 3.3. So you can easily calculate our input, and we will find that our input will be equals to, let me tell you, 2.33 mega ohm. Herein, there is a very important question. Maybe while you are solving the circuit, you ask yourself, why we insert this 10 mega ohm? Because this 10 mega ohm is neglected in the DC analysis, if you remember. If you remember in the, yes, I think that I have it somewhere. In the DC analysis, yes. In the DC analysis, we have neglected this 10 mega ohm because the current was equal to 0 in the gate. And in the AC analysis, as you can see, the V output is independent on the 10 mega ohm. We calculate the V output as the current flowing here multiplied by the combination of these three resistors. So it's also neglected, or it's not considered, I mean. So why we insert this 10 mega ohm? We insert this 10 mega ohm for this reason, to have a very high input resistance. Please don't forget the ideal operational amplifier in chapter number 1. We should have a high input resistance in order to avoid the loading effect of the source of the source resistance. So that's why we have here this 10 mega. Maybe you can resolve the problem again 2 times. The first time is with considering this 10 mega ohm as an open circuit. So the gate and the drain are not connected together. However, in this case, you should assume a DC input biased to the offset, because the DC gate voltage, if you recognize, came from this link. So if you open circuit this link, this gate will be without a DC component, which is what we illustrated in the beginning of this part, and the MOSFET will not work. So we have to have a DC offset here. The second is to consider this as a short circuit, like the current mirror, and to see the effect. By the way, one of the reasons why we don't use a DC voltage here and we get the DC biasing from this branch is that we are using this capacitor, because this capacitor will not pass DC components. So if you put a DC capacitor here, sorry, a DC biasing here, you should get rid of this capacitor. Otherwise, this DC voltage has no effect on the circuit. This is very important. So this is example. We are going to solve more examples in the tutorial problem, and maybe we are going to solve also more examples in our extra session if possible. But please don't forget that this is a very important example, or this category of problems is a very fundamental in your final exam, inshallah. So this may be considered as the termination of our MOSFET lecture. But before termination, one more application I will just demonstrate it in a very quick manner, which is the application of the MOSFET as a switch. In this part, we consider the MOSFET as an amplifier, or I can say that this is an analog amplifier, which is the analog application of a MOSFET. However, in digital electronics, we are using a MOSFET as a switch, which is the basic concept of a switch. It's an on-off switch, as you can see. It's very simple like that. If you supply the gate with a voltage greater than V threshold, then that means that the drain and source are connected, because the current flowing in the drain is typically the current flowing in the source. So your switch is connected. If the voltage supplied to the gate is smaller than V threshold, that means that the current flowing here is zero, which is now the switch is an open circuit. So the most famous integration of the MOSFET in digital electronics is to work as a switch, on-off switch. Just to give a VG greater than V threshold, your MOSFET is on. To give VG smaller than V threshold, your MOSFET is off. And this is actually the key parameter in implementing all your digital devices, all your digital gates, logic gates, and doors and all this stuff. Maybe you will know more about that in your fourth year course, which is the VLSI course, in order to investigate more about the implementation of these logic gates using MOSFET. This is the termination for chapter number 3. Our next and final chapter will deal with what's called the bipolar junction transistors, or the BJTs. So see you by next lecture, inshallah, and hope you enjoy your weekend. Thank you very much. See you later.